All right, so in this problem, and they kind of set you up here, they tell us that bacteria can multiply at an alarming rate. So you're expecting it to grow very fast. All right, we're starting off with 5 bacteria, and we want to write a function if it's splitting into 2 new cells, and so doubling every hour. We would have a function now using the appropriate notation. Now, personally, again, I like y and x, but they're telling us specifically to use b and h. So we got to go to b and h for this. I know, it's a lame joke, but
It's a store.
yeah.
Alright. You just find new ways.
I don't.
I mean, he's automatically got an A in the course now. So, like, I mean, that's really good done it. So, anyway, this is our function, but I don't want to think of it that way. So, in the calculator, we would say y equals 5 times 2 to the x power. All right. Now it's asking us to determine how many or how much bacteria would be at the end of a day. So it's 24 hours. So I need y of 24, which is going to be pretty big. All right. So we'll go to the calculator for this. Now this is a simple calculation, so I can go to the TV. 800 and
83,886,080.
Really no.
so lots and lots of bacteria after one day.
Nice.
So
Great.
here's an example, real life example. We talk about bacteria, right? Anybody ever have strep throat?
Yeah.
Yeah. Okay. You don't have it now, do you?
No.
Yeah, thank God. It's like, like I've never been more frightened in my life. Like everybody. Yeah, I know, but like the thought that I was in a room right now with 20 people who had strep, it's like it just freaked me out for a second. So, yeah, so they stuck the cotton swab in your mouth, they put it in the back of your throat, and did a little, you gagged, and they pulled it out.
I hate that so much.
They went into the other room, then they came back like a minute later, maybe 5 minutes later, and said, "You got strep."
Or they say you might not have strep, and then they're like, we'll let you know in 24 hours. 24 hours later, you find out you have strep.
Right. And so I didn't really know this because like I just focus on the math. Like I don't really consider too much about the real science behind it. Or at least not when I was in your position. But something that my son's doctor said actually got the wheels turning, and it made me think about it. So she said, "All right, we're going to do a strep test. We'll be back. I'll be back in a few minutes. I just need to go and see if it grows strep." And just the fact that she said to see if it grows strep, I was like, that's a weird thing to say. Why did she say that? It's because she took a sample, skin sample, saliva sample, whatever it is, and then they tested the growth. Right? And after a certain period of time, you can make a determination of whether it's going to grow enough population to indicate that a person has the infection. Right? That's why they have the overnight. So they do the rapid strep test, which is where they accelerate the growth, but that's unreliable. But they also take a sample and let it grow naturally over a 24-hour period to see if it grows to the appropriate population to indicate that somebody has strep. All right, so this example here is the strep test, basically. Nice. All right, so when you see this number, you're talking about a population of bacteria that grew from only 5. That's pretty insane. All right. Now we had the added bonus of, all right, well, we're going to test for the flu and we're going to test for strep, and so he sends. This was a different doctor. He sent out all the stuff to get analyzed, and he starts talking to me about like the course of treatment. And so he said, okay, well, we'll start treating the strep because that's most likely what it is. All right. And so if that's the case, then, you know, like, we'll be simultaneously treating the symptoms of the flu, because it was one or the other. So he tested for both, and then the nurse came back a couple minutes later. He confers with the nurse, and he said, oh, forget everything I just said. He's got both. He's got the flu and strep. You remember that, right? So it was like, all right, well, now we have to treat the bacterial infection because the flu is going to work itself out. That's just got to run its course. All right. So, yeah, but this is how they do it. Now, they have physical apparatus that they use. They actually, you know, like, test it. They have to perform science on it. But this is the underlying math behind that science, and it's pretty cool. All right. So, how long would it take to reach 1 billion bacteria? That's where the calculator comes into play. All right. So, what we're looking for is the solution to the equation of 5 times 2 to the x power is equal to 1 billion. So that's what, 9 zeros?
Yeah.
Examples.
Yeah. I mean, in math, history was a different story. Most history classes I took twice. First grade would be the W. The second grade would be usually something pretty decent. W for withdraw, which is kind of like a drop, but with consequences. So, yeah, history and I did not go hand in hand. So anyway, after all this talking, I didn't take note of what the actual answer was. It was
27.5 or something.
27.5. 575? All right, well, let me just get it because we want to go 3 decimal places. Math solver. Fortunately, it's very easy to do with this nifty solver approach. 0.575, okay. All right, so not too bad. All right, so that's hours. Which is really kind of gross when you think about it. All right, so now we're going to switch over and talk about a different exponential function. 8 times 2 to the x power. Create a table of values, which is not difficult because you can just go into the table. These are convenient numbers. So I'm not even going to display it. I'm just going to type it in and look at the table. So we're looking at a half, 1, undo apparently. That jumped. 1/2, 1, 2. So we're just doubling. 4, 8, 16, 32, 64, and $1.28. All right. Now, in terms of the notation, nothing too crazy here. I just wanted to take a second and talk about what each part of this function represents. The 8 is the coefficient. And we generalize this later on somewhere, but I'm going to start using these terms right away, so I want to get it out of the way here. That's the coefficient. The 2 represents the base. And the x is the power or the exponent. Really, just so you have an idea of what I'm talking about when I say these words. All right. The most important part of an exponential function would be the base, all right, because that really dictates the type of growth or decay that we're looking at. All right. The power of the exponent, it's not always going to be an x, so we'll have to make adjustments in our thinking when we get to that. But generally speaking, that's going to relate to some kind of transformation. All right. The coefficient of 8 doesn't really have as much of an impact as you might think. In fact, if you were to graph 8 times 2 to the x and 5 times 2 to the x side by side, you would see a little bit of a difference early on, but not much difference for extreme values of x. As it gets larger and larger, it doesn't look very different at all. All right? The only place where it does look different is right around the y-axis. All right? So for this problem, all we're doing is creating a graph on paper, but we have to kind of live with the scale that we're dealing with here. So we're going in the x-axis, we're going from -4 to 4. That's easy enough. So I'm just going to go by ones. So I'm going to chop the intervals in half and then half again. I suppose I could do the same thing on the y-axis, but when I chop it in half, I get 65. But then I chop that in half again, I get 32 and a half. I don't want to deal with decimals there. If I look at the types of numbers that I'm dealing with here, they're very small initially, and then they spike up. But more importantly, they're not really living in any kind of particular realm. Like, they're not all, well, I guess they're all even. So aside from the 1/2, that's the one thing that we can deal with. But I don't want to go by 2s just so I can have exact points. So it really doesn't matter what you go by. You can go by 20s, but 20 doesn't go into 130 evenly. It seems like 10s would make the most sense.
Can you make like a 128 mark right below the 130 and then start splitting it in half?
You could.
That's fine.
Yeah, that's a good idea.
And Tyler.
And in fact, I was going to say, let's just change the scale. It kind of defeats the purpose of the question, but it would be just so much nicer if that was a 128. I kind of want to make it a 128.
Let's do it. No regrets.
Yeah.
Yeah, Tyler.
We do not conform to society.
I know, it came from there.
64, 32, 16. I don't think I could physically write a 2 in there, so we'll just have to believe it's there. All right, so we're actually creating the beginnings of what would be called an exponential scale. It's very similar to a log scale. I don't know why I said that. Yeah, we've not talked about logs yet, so it doesn't mean anything. All right, so anyway. It's just basically a scale where your axes are in terms of powers rather than numerical values. Or they're all numerical, but integer values.
So you can't do like a square root with a translation to the right.
Why?
Because it's square root of x minus whatever.
Right, but if x is like, let's say, 3 and you're only subtracting 2.
All right, so the first value was a 1/2. Now, plotting that is as simple as saying, all right, it's really, really close to the x-axis. I don't know where, so I'm just going to make it really, really close to the x-axis. All right, the next one is 1, which is a quarter of this distance or half of that distance, which is still like a smidge away from the x-axis, but just a smidge more than the point that we plotted at -4. I think you got it. Then we have 2, then we have 4, then we hop up to 8, then 16, then 32, 64, 128.
Yes, Tyler, it is a graph.
I don't know, that would be so sassy.
Dude, I was just letting Tyler know it wasn't a graph.
Seems like there's a little bit.
Now, you don't have to label, if it's just a single curve on a graph, you don't have to actually label the graph because it's obvious what it is. But I'm labeling it here because I wanted to just point out something very quickly. We notice we have a coefficient here of 8. Where else do you see 8 on this graph?
Oh, 0.
At x equals 0, the y-intercept. All right? So that tells us, at least it seems anyway, that that coefficient is also the y-intercept. It turns out that that's the case. All right? It will always be the case. Yeah.
Look at how that
Oh, that's so nice.
Whoa.
And mathematically, it makes sense because if you're on the y-axis, the x value is equal to 0. What's 2 to the 0th power equal to?
0.
1.
1.
Oh, yeah.
1 times 8 is 8.
We went over this the other day.
All right, so second problem. Same general idea, we're going to get some points from the calculator, but you can see now you have a fractional base. We're using that term base already. So 54 times 1/3 raised to the x power. This time we're only going from -2 to 4. So cleaner window, which is kind of nice. So we're talking huge. Look at that. It's crazy. 486. 162. All right, so you could see here that there's an insane drop early on, but then the rate of decrease slows down. All right, so you fall off a cliff initially, but then it's more of a soft landing later on. All right, trying to think. I think it was at Great Escape Water Park, also Kalahari. They have one of those. It was actually, I believe it was this graph that was probably the inspiration for that water slide. It's the one where you stand in the tube and it has a trap door.
I love those things. And then
I will never go on that.
yeah, it's awesome.
Yeah.
That's the best
That's
thing
a
ever.
nightmare. I would never do
You
that.
stand and then the door shuts on
It's like an enclosed space. and
Right.
it's like-
So awesome.
That
I've never been to one.
That's the best thing you
so look like that, roughly, something along those lines.
Wait, what do you make your, what are you gonna make our, like a minute max for?
That's the question. So x is good, right? We don't have to worry about that. We know we're going from -2 to 4. We can scale that. We'll do that in a sec. We're not going below the x-axis, so the y-min should be 0. Now, I give a little space below the x-axis so you can actually see the x-axis, but what's a reasonable value that's close to 486? 500. All right, so you want to have a nice value close to your max,
Go by 100.
but it should be larger than your max. So if you choose 500, then it allows you to go by hundreds. All right, so I'll put 500 somewhere up here, wherever I want, and then I just have to break this up into fifths. So 1, 2, oh, nope, 2, 3, 4, 5. All right, and then I have -2. Half the distance is -1, so I have a little bit of a sense of the scale here. So 1, 2, 3, 4. All right. Now, if you want to go by 50s, you want to break it down even further, you can, just to give yourself more of a sense. So I can say, since I have the 100s, I could break it up even further and say 50, 100, 150, and so on. I'm going to label them all, just so I don't have to count. All right, so -2 and 486. So it's somewhere between the last two tick marks, closer to the last one. -1 and 162, 54, 18, and then, well, really the last few, you're ballparking it, but you're doing it in such a way that it's getting progressively closer to the x-axis. So it's not exact. I'm not sitting there with a ruler measuring your distances. All right. All I need you to do is make sure that the next point I plot after 1 is closer than the one at 1, and the next one at 3 is closer than the one at 2, and so on. Or at least it's reasonable enough to assume that that's the case. So just zoom in on your paper real closely, and you'll be able to do it fairly easily. And then, zoom out. And then with the world's shakiest hand, draw your curve. Alright, so peak drop early on, and then it levels off later on. Alright. Now you don't always have to label your equation, but I'm going to do it now. The only time you really have to label it is if the directions, first off, tell you to do that, and second off, if you have multiple equations on the same graph, multiple functions on the same graph, not including piecewise. All right, so yeah, I knew I had it in here somewhere. Exponential function, so just to generalize, and so you have a place where it's all written, has the form of y equals a times b to the x power, where a is the coefficient, b is the
No, we didn't.
yeah, it's like
Got it.
No, I already got like 7 minutes ago. I already saw it from. Sometimes I do that. Hold up. Have you already got that?
I didn't
No,
bring it
I didn't get
to
that one.
school today.
Why?
I kind of just forgot.
X is known as the power coefficient.
x is known as the power for the or the
Why did I say
exponent.
efficient?
Did I get it? Anyone claim that? I claim it.
All right, increasing exponentials, they go uphill.
Wait, if it's less than 1, it's decreasing.
If it's between 0 and 1. So if b is greater than 1 is the increasing. For decreasing, it's between 0 and 1. Alright, so there are some weird conditions that come into play, like for example, some might ask, well, what happens if the b value is negative? It actually works out that you can simplify it in such a way that you can pull the negative out. So that becomes irrelevant. Quick question, what happens if the b value is equal to 1? If I were to replace the b with a 1, what would this simplify down to? Not 0. Just a. Because 1 to the x would be 1, because 1 to any power is 1. So it wouldn't be an exponential function anymore, it would just be a horizontal line. Alright, so we don't have to worry about b ever being equal to 1 because it wouldn't be an exponential function anymore. Alright, it would still be a function, just not exponential. Alright. Now for these kind of problems, they're asking us to analyze it a little bit. For each of the following exponential functions, give its y-intercept and tell whether it's a growth or decay. Well, the growth or decay part is really easy because all you're doing is you're looking for a number that's either between 0 and 1 or greater than 1. All right, so we'll start with that for each one of them. Is A growth or decay? Decay. What about B? Growth. And C? Growth. Yeah, it's the same number, just written in a different form, right? Now, let's go back for a sec to the graph here. So, what was the y-intercept for this graph? 54. All right. What was the coefficient for our original function?
54.
54. All right. On the previous page, what was the y-intercept? 8. What was the coefficient? 8. Okay, so what are we getting from this? Coefficient is the y-intercept. All right. So what's the coefficient for A?
8.
So y-intercept is 8. So then you get it, 125 and 56. So y-intercept, 125, y-intercept, 56. Now, if you were ever to forget that little relationship, no big deal, because you could just go into your calculator. What x value does the y-intercept always have? 0. All right, so you just go into your table of values, look for the x value of 0, find the y that goes along with that. Or plug 0 in and solve. Yeah. All right, so it's nice to know these relationships, but if you don't have it memorized, your calculator's your best. Oh, so, all right. So, on the next page, we get into, because this is important stuff, the domain and range, it keeps coming back over and over again. It's one of those things where it's like, man, we're still with this domain and range business. Yeah, it's never going away, so we have to get into it. All right? But the good news is, just like we had transformations for the functions in previous units, we'll have transformations for this. So if we know the domain for a parent function, then we're going to know the domain for the transformed functions. All right, so that's what you need to take some time to figure out. But before we get to that, number 4 is asking us to find the equation of the exponential function in y equals a times b to the x form for the functions given in the tables below. Sorry. So really, you need to determine 2 things. You need to determine the y-intercept in A, which is what? Y-intercept is equal to 10, so therefore the A value is equal to 10. And then what we need to figure out is the multiplier. All right, from one step to the next, what are we multiplying by?
1.5. 3? Oh, no.
3, yeah. So to get from 10 to 30, 30 to 90, and so on, we're multiplying by 3. All right. So we know that the b value is equal to 3, and so we're looking at an equation of y equals 10 times 3 to the x. All right. For the second one, y would be equal to 800. You got to figure that part out first. Times 1/2 to the x power. All right. I guess I don't need that dot in there, but I'm going to leave it anyway. All right. So
for an exponential function, domain and range, the good news is the domain is all real numbers. All right, we looked at enough graphs to know that it doesn't stop anywhere. It doesn't turn around on itself. It goes to the left, it goes to the right, and it doesn't skip anything in between. So negative infinity to infinity.
Always?
Always.
Okay.
All right. The range is a different story. In each one of those graphs, did we ever hit the x-axis? No. All right. Did we ever go below the x-axis? All right. No. So the negatives are out and 0 is out. So what should my range be?
1 to negative.
Yeah, but like that's so it would go up to positive infinity. But what about like a half? Is a half okay? A quarter? An eighth? So 0.00000001? I don't want to write that.
We can't be 0.
Can't be 0.
Less than 0.
0 with parentheses, yeah.
Wait, what? Oh.
That gets us close to 0 without touching it. All right. How did we know it was going to be increasing before we graphed it? Bearing in mind that we didn't even graph it yet, so we really need to know, based off the function, that it's going to be increasing. What about this function tells me that it's increasing? Yeah, the b value is greater than 1. All right. So number 6, domain.
Negative infinity to infinity.
Negative infinity to infinity. The range. 0 to infinity. All right, and how do we know it was going to decrease? B is less than 1. All right. It's not bad. It's not bad.